welcome everybody to this year's Invasive blood pressure project. We have 4 teams this year, and this is Team Balance, managed by Jeff Burchell. So judges have, well, most of them have judged this project before, so they know how to do it, instructions and everything that you need to know. So I think, Jeff, you can make it away.
Very well. Hello everyone, my name is Jeff Burchell and I am the manager of Valence Medtech's Invasive Blood Pressure Monitor Project. Valence Medtech is myself, Mo Weeva, Ethan Slynn, Aidan Snitson, Kush Dalwadi, Jijo George, and Mitch Colbert. I'm going to start off with introduction about blood pressure and invasive blood pressure monitoring. Then we're going to go to functional tests, amplifier design, calibration signal, readout, simple quality upgrades, feature upgrades, miscellaneous, and then I'll do a conclusion. So as we go through the presentation, the sidebar of the PowerPoint will show you what section of the presentation we are in. So to start the introduction, what is blood pressure? Blood pressure is the force of blood pressing against the walls of the blood vessels. Your heart contracts to pump blood around the body and then rests in between each heartbeat. Units of measurement. When you get your blood pressure taken, 2 measurements are made. The upper or systolic pressure, the lower or diastolic pressure. For example, 120/80. Pressure is measured in millimeters of mercury. That is the height in millimeters of a column of mercury the blood pressure could support. Systolic is the pressure in the artery as the heart contracts. It is the top higher pressure, for example, 120. Diastolic is the pressure in the artery when the heart is relaxing, filling with blood. It is the bottom lower pressure, for example, 80. Charting the blood pressure. So here's the heart in systole, so it's contracting. The blood is being pumped out of the artery, and you can see that's the peak of the blood pressure. This is time running this way. This is millimeters of mercury running this way. And this is it in diastole. It's relaxing. Blood is filling in, and that's the trough. Non-invasive blood pressure. We are all familiar with getting our blood pressure taken non-invasively. The clinician can't see the waveform, but can tell by sound through their stethoscope when to take a measurement to get the peak or systolic pressure, and when to take a measurement to get the trough or diastolic pressure. Invasive blood pressure monitoring. We are interested in seeing the actual waveform, acquiring it, amplifying it, and displaying it. How do we do this? This is how we do it. A tube, intra-arterial catheter, is inserted into an artery. It's right there. The catheter is connected to the transducer and a saline-filled IV bag with a 3-way connector and tubing. So here's the 3-way connector. So we've got the tubing coming from the artery. There's a saline bag, IV bag, and there's the other tubing that runs right to the transducer. The tubing and transducer are filled with saline solution from the IV bag, purging the line of any air bubbles. The tubing containing a continuous column of saline conducts the pressure wave created in the heart directly to the transducer. So essentially, the heart is creating pressure waves, almost like a sound wave. The pressure wave travels down the artery, through the tube, and into the transducer. The IV bag of saline provides a continuous slow flushing of the system. Flushing prevents blood clots and purges bubbles, which would interfere with the correct measurement. So this is under some pressure. There's a continuous slow flush of the entire system. The transducer. So the transducer's pressure dome is filled with a saline solution connected to the tubing that is carrying the pressure wave from the heart. The diaphragm of the transducer acts like a microphone, converting the pressure wave to a small electrical voltage. As the diaphragm moves, the voltage increases and decreases. So this is showing the transducer undone. So basically, this is the pressure dome. There's the diaphragm, and this entire piece here would be filled with saline. You have the pressure wave running in, and then the diaphragm would be responding to it, much like a microphone. And as the diaphragm is moving in and out, it's producing a micro voltage going up and down out here. Amplify and display. So that's what we want to do. So we've got the pressure wave coming from the heart through the artery to the tube. It's to the transducer. In the transducer, it's changed from pressure to an electrical voltage. Right here, the electrical voltage is very small, so it's just in a tiny voltage. And in the processing unit, it's amplified so that we can display it. Here's a commercial vital sign monitor, and you can see, maybe you can't see it, but right here is the invasive blood pressure. And this one is 132/73. What does the transducer give us? The transducer puts out a signal in the millivolt range. For example, 80 millimeters of mercury of applied pressure could give 8 millivolts. We have to amplify this small voltage to produce a strong noise-free signal for display. For example, we could amplify this 8 millivolt by 100 to give 800 millivolts. We could then display this 800 millivolts on the monitor, labeling the y-axis as pressure instead of voltage. So if this is time and this is voltage, sort of like on an oscilloscope, we can just be tricky and change this axis to millimeters of mercury. So that's essentially what we're doing. Calibration 0. A pump and pressure gauge can be attached to the transducer for calibration. If 0 millimeters of mercury is applied, the transducer being essentially open to the atmosphere, the transducer will probably not produce 0 millivolts. It will produce a small voltage, like an offset, for example, 1 millivolt, which will be amplified to a larger voltage and displayed as a line, for example, at 10 millimeters mercury. The line has to be brought down to 0 using a zeroing knob. So just because the transducer is like it is, if you open it to the atmosphere, and so that's sort of setting the stage, it's going to give you a line like flat line, say right here. And so what we want is a knob we can adjust, and we can bring that flat line down here. Calibration adjustable gain. Once the zero is set, the gain has to be adjusted. For example, the pump is pumped until 80 millimeters mercury of pressure is applied to the transducer. The transducer will produce a voltage, for example, 8 millivolts. We want to amplify this to the proper amount, so it's displayed as 80 millimeters mercury on the monitor. For this example, we would adjust the gain to 100 times, giving an 800 millimeter output displayed as 80 millimeters mercury line on the monitor. An adjustable gain knob is to use this. So essentially what we do is we take this pump, we pressurize this till we read that it's 80 millimeters, and then we adjust the gain until we see the line come up, because it could be like, it could start off, could be here, or it could be here, and we use the adjustable gain to calibrate it right directly to 80. Why invasive blood pressure? Accuracy, it's dead accurate. Continuous beat-to-beat monitoring for patients who are likely to display sudden changes, for example in surgery. Allows blood pressure readings at low pressures, shock patients. The trauma of repeated cuff inflations is avoided in patients who need close long-term monitoring, like in ICU. The shape of the trace can be interpreted by eye for diagnosis or by a specific device. It can be analyzed by a computerized device. Use of a simulator. So we don't use an actual transducer, and so what we use is a simulator. It simulates the output of a transducer hooked up to a patient with a normal 120/80 millimeters mercury waveform. It also produces static 0 millimeter, 80, 120, etc. signals for the purpose of calibration. Team Balance's job: to engineer, design, and build an invasive blood pressure monitoring device which is able to acquire the blood pressure signal from a transducer or simulator, zero, amplify, and correctly display this as a noise-free blood pressure waveform of the correct amplitude, process the analog waveform in order to capture and display the systolic, diastolic, mean arterial pressure, and beats per minute values. I'd like to welcome Heath Phillips, and he's going to talk about functional tests.
Thank you. Hi everyone, my name is Heath Phillips, and I'm going to talk about some functional tests. And which is going to be up to me, showing you like turning on the device and making sure that it can be used and so on. So I'm going to go through some theoretical stuff first about the gain, bridging of what Geoffrey was talking about. From biomedical perspective, gain produces accurate amplified output voltage of the pressure transducer and also controls amplification of the output voltage. From clinical perspective, gain increases the amplitude of the blood pressure waveform, which makes it better visual quality. Zeroing is very important when you're doing INDP examination. From biomedical perspective, zeroing up in the fluid, up in the fluid column of the transducer to atmospheric pressure, so it becomes the starting point to the examination. From clinical perspective, we should always zero the display and the module or simulator working on to avoid any alarms. Like some monitors in the market will give you not zeroed on the monitor, so you can't do the examination unless you zero. Like you zero the offset actually, and then also it confirms that the transducer is working, and it leads to accurate blood pressure results and establish an accurate zero point. Would you wish to show me?
So as a clinically, when the nodes usually connect the machine to the patient with the transducer and with the blood pressure cuff on it, and in this case we have a patient simulator. So first procedure nurse do is zero the pressure signal, and first they open the stopcock to the atmospheric pressure, and they zero down that atmospheric pressure to zero. So usually supposed to press the zero from here, so the signal will zero, and like we can control the manual zero from the manual zero adjustable control, and then like with the waveform we can increase and decrease the gain for the better resolution too. At the moment, like if I press the zero and try to adjust the manual zero, this might affect our alarm to go like up and down. So like we're gonna like demonstrate it in the final demo with the zero and the gain, and demonstrate the alarm too.
Thank you, Coach. So I will leave a slide for you to talk about amplifier design.
I'm going to be explaining section C, amplifier design. So the core of the machine is to acquire the signal from the patient simulator, and the main basic is a transducer, which is a Western bridge. So in this case, we have a patient simulator as a Western bridge, which requires the voltage from the machine, and it kicks the output with the pulse waveform. So it takes the like very tiny small pulse signal, with the less frequency response. And amplifier amplifies the voltage and reduce the noise too. So it is very important when we are trying to design an amplifier circuit to select proper instrumentation amplifier. So we have selected 2 stages to design to acquire our pressure signal, so that it changes instantaneously with the change in the pressure from the vacuum simulator. So the circuit is the 2-stage amplifier design. First stage we have constant gain amplification with the use of 8620 instrumentation amplifier, and the second stage consists of two amplifier, one for inverter with the adjustable gain pot, and the second is with it's a unity gain inverter to display the waveform in a proper manner. So stage one consists of 8620. So main purpose to use the 8620 is its characteristic, which is compatible for pressure signal, because the pressure signal is has very slow frequency response. Its frequency is almost less than 2 Hz, and it's a small microvolt signal, so it needs the amplification. So 8620 is compatible. It has a good input and output characteristic, and it does not affect the tiny signal. It is amplifying. Its output signal is not easily dragged down by downstream circuit too. So like once the 8620 acquires the signal, rest of the circuit will follow the signal too. So it does not affect its nature. It's going to affect the nature of the signal. The 8620 has a good slew rate, and it's a change with the change in the input signal. It's gonna change instantaneously, and it's gonna reduce the noise too. And noise is basically reduced because of it has a good common mode rejection ratio, which eliminates the 60 Hz noise. So 8620 frequency response is almost in between 0.2 Hz to 150 Hz. So which is very compatible for the pressure signal, because pressure signal is almost less than 2 Hz. So it's gonna allow the pressure to pass through the 8620 and acquire the signal in a proper compatible manner, because sometimes unwanted frequency from outside might affect the characteristic of the input frequency. So it has a wide range of gain too, which can be controlled from 1 to 10,000 of gain. We are using it right now, we are using it with the fixed gain of 100. So we're gonna amplify our pressure signal with the constant gain, and then we're gonna control with the offset, we can control the zero of the pressure signal right at the 8620. It is made to null the acquiring signal. So basically at the pin 5, we can control the zero line. We can from the +5 to -5. So depending upon the requirement of the pressure signal, we can control the offset. The second stage, once the pressure signal gonna amplify with the constant gain, we can control the gain up and down with the adjustable gain. So we have one inverter amplifier, and with the pot we can control the gain up and down. Clinically, it gives a faithful reproduction of the input waveform, has a low noise, and it is easy to adjust the gain and 0 to the faithful reproduction of the waveform and easy of use. Correctly setting the gain and 0 are critical to correct patient monitoring and diagnosis. So, and this is the main circuit. So basically, the circuit has excitation, and it takes the output from the patient simulator at the signal in, the waveform in. So signal comes in from here, and it goes to 8620, and it gives a constant gain with the constant gain resistor, and it's going to amplify the pressure waveform to the constant gain, and then that second inverter will control the pressure signal, amplitude of the pressure signal up and down, and that pressure signal can go to like output and will feed it to all circuit. So I want to introduce Mo, who's going to explain internal calibration. Thank you.
Hello everyone. My name is Mo, and I'll be talking about the internal calibration circuit signal. So to start off, what's the importance of the internal calibration signal? So basically, with this idea, what we do is actually we inject some known values projected to the input of the instrumentation amplifier, and by reading the output of the signal at the display, we'll be able to compare the input of the input which is known, static, and accurate signal to the output of the instrumentation amplifier. So basically in this circuit we have 4 different modes. We have the 0 line, and we have the 100 millimeter mercury, we have also the 150 and the 200 millimeter mercury. Now for the clinical perspective, now why the clinician or the nurse like the doctor would be actually interested to know about the calibration circuit. The 0 calibration is basically used to adjust the 0 line. So before starting and using the machine, it's very important actually to zero the line of the signal and to make sure that we have the 0 line. So having the 0 line basically will refer the reading of the systolic and the diastolic to this 0 signal. The other important part is basically to compare the dynamic sine wave, which is the blood pressure signal, to these value. For example, like the nurse, it can compare the dynamic signal, which is the blood pressure signal, to 100 millimeter mercury. That can also compare to 150 and 200 millimeter mercury. And in this case, it will verify the gain of the instrumentation amplifier. Now we also use the digital switch, and the digital switch will actually flip and cycle between these modes. So basically the first mode is the dynamic sine wave, the second mode is the 0, and the third is 100, 150, the fourth, and 200 millimeter mercury is the last one. And why is the calibration important for the biomedical technologist? Now, using this calibration circuit, by inserting this static signal to the input and the instrumentation amplifier and reading the output at the display screen, will be able to verify that the signal acquisition circuit and the systolic and diastolic circuit are actually working in the proper way. We have this, this is the schematic diagram of the circuit, and we have the calibration circuit basically on the right side. We have the excitation circuit on the left side, and we actually used one board like to make all these 3 circuits on one board. And the rest of the components basically are the combination of the digital switch. We use the counter, we use also decoder, we use inverter, CMOS switches, relays, and then at the contact, these contacts basically will be connected to the calibration circuit, and they will pass the signal to the signal acquisition circuit. Now we created a small animation to understand the theory behind the digital switch. So basically what does this digital switch do is to take the signal, which is known, from the pots, from the voltage dividers, and then pass it to the signal acquisition circuit. So So the first part we have the counter, the 7490, which is 4-bit counter, and we're using only 3 bits to make it count mode 5. We also have the decoder, and the decoder will basically decode the 3 bits, and it will create the 5 bits. Now this decoder will provide us with 5 different bits, and it will pick 1 bit at a time. So as we can see, the first bit is actually low in this case, and this bit basically it will be applied on the inverter gate, which is 7404. Now the function of this inverter gate is to invert the input, and as we can see, the output of this inverter gate, it will be high, it will be 5 volt. Now this 5 volt, it will be applied on a CMOS switch, and it will trigger the enable pin. Now triggering this enable pin, it will close the switch. Closing the switch will pass 5 volt to these relays, to the relay coil, and these relay coils, they are rated for 5 milliamp. It's very like low current, which is very important to work like with these type of switches. Now when we have the relay coil is energizing this relay coil basically will close this contact. And this is basically we have it's not like only one contact, we have different contacts and different relays. Closing this contact will pass the signal from the voltage divider through the contact, and then it will pass it to the signal acquisition circuit, which is the input of the 8620. Now, once the signal reaches the input of the 8620, we will be able to see the result on the display screen. So, as we explained earlier, that this is actually like this is the operation of one mode, and we have 5 different modes in our circuit. So basically the same operation, it will happen when we switch and when we recycle using the counter 7490. So as we can see, this section over here, this is actually the 5 different modes. And we have this push button. Now, this push button basically, it will recycle the counter. And the first stage, as we can see, is the blood pressure monitor, which we can see it on the screen. The second one is 0, and we have actually to use this 0 basically to use like the 0 line for our circuit. And we also have the 100, 150, and 200 millimeter mercury for the calibration signal. And now I would like to invite Eamon to speak about the readout, section E.
Thanks, Mike. That was a positive presentation. These things always get me. But everybody take a deep breath. Because when you sit around for a while, seriously, like your blood pressure drops. You don't get enough oxygen to the brain. You're not as much work as you should be. These are highly technical presentations sometimes, and it might be a little too distracting. So it helps me too. Thank you. It's all about blood pressure. How your blood pressure. Adding more oxygen to the brain, more alertness. Now I'll talk about readers. Right. Go backwards. Okay, so over here you can see on the screen to the far right that we do have a readout on a simple and easy to follow screen. It's an LCD display. It's a touch display, and they're clearly labeled with systole, diastole, MAP, which is mean arterial pressure, and BPM, which is beats per minute. And the values for each of those are found directly underneath. So the question usually comes up, systole, diastolic, or MAP, which one's the most important? There's a lot of research that's been done. I think the most recent one we found was the University of Cambridge, which says systolic is the most important. Look back 30 years, people are saying systolic. There's no clear-cut definition. In my mind, I'm not a professional as of yet, but I'd say mean arterial pressure gives you a good range to look at to start for diagnosis for the patient or someone that may be having, say, a rather large systole, or quite low. These could lead to heart problems or further health issues later on in life or during the checkup. So right now on the display, all of our outputs are within a range of plus or negative 3 millimeters of mercury. This is specified in the outline, so we have to adhere to these standards. But in the end, we were able to design an output that is within 0. So it's accurate. It's to do with the programming as well. We'll talk about that later. So the Arduino programming library links to the screen, and that simplifies also the troubleshooting of the system. So there's strict logic that has to leave from all the circuit boards and go through an Arduino. The Arduino will pass that through a coding, and that coding will determine if the output on the screen will be what it is. So for example, 120/80, there's a range that it has to hit, and it's a very tight range, and it falls between that range, it will hit 120. This is why we say that we're within range of plus or -3, but we're actually 0 on the screen. So I'm going to pass this back to Mo, and he's going to continue talking about the systolic and diastolic. And
so the systole and diastole basically are the most important part of the blood pressure monitor. They are very important for the clinician, part for the nurse, and they are also very important for the biomedical. Now the systole is basically the pressure that's applied from the heart when the heart is contracted, and this pressure is basically applied on the veins and the arteries. Whereas the diastole is the pressure that's applied when the heart is actually relaxed. So for example, like for the ventricles of the heart, they will be like so they will be contracted in the systole, whereas they will be filled with blood in the diastole. The blood vessel also they will be contracted in the systole, and they will be relaxed in the diastole. Now the systole, we know that it's normally the higher number, the higher range in the blood pressure, and then the diastole is the lower number. Now the range of the systole is basically from 90 to 120 millimeter mercury, and in this case the patient will be like okay with no problems, no diseases. And the diastole is basically from 60 to 80 millimeter mercury. One more time, why is it important for the nurses to actually know like the values of the systolic and diastolic blood pressure? It's very important so they can diagnose the patient's situation. They can look at the heart of the patient by three elements. They can look at it basically by the ECG waveform, by the blood pressure signal, and then by the heart sounds. So basically they can diagnose like the situation of the heart. They can detect if there is any pre-hypertension, primary hypertension, secondary hypertension. And the systole and diastole, they are also very important for the biomedical technologists. So for example, the biomedical technologists basically will perform some troubleshooting based on these numbers. So for example, if we can say that a patient is basically has no problems with his heart, and then suddenly the value of the systole or diastole like it jumped to 100, 140 or 160. So in this case, we will detect that something is wrong with the device, and we have to perform some troubleshooting basically. Now, this is the schematic of the systolic and the diastolic, and the schematic is actually perfectly working. So basically, we have at the top is the systolic part, and the bottom is the diastolic part. So the systolic part basically it's a positive peak detector circuit, and we run the signal. Basically, we use 555 timer to control the 7476 JK flip-flops. These JK flip-flops basically will control again CMOS switches. The CMOS switches will be connected with capacitors, and the GK flip-flop will control these switches. Now, opening and closing these switches basically will cause these capacitors to charge and discharge, and then right after the signal basically from this capacitor is passed to buffers, and then the output of the systole. Now, we use the same circuit with the diastolic pressure, but we had to do some technique basically. What we had to do is we had to, first of all, invert the signal, raise it up by 2 volts, and then pass it through the same circuit as the systole, and then the output we had to subtract it again by 2 volts. I'll just go with a very quick demonstration of the device. So basically on the display screen we have this number over here, which is the systolic, and we can see that right now it's 120, and the diastolic part basically is the lower number as we mentioned earlier, and it's actually 80 millimeter mercury right now. So now I'd like to call Mitch to speak about the simple quality upgrades.
Good afternoon, everyone. I'm Mitch. I'm going through simple quality upgrades. This is section F, and what I'll be basically doing in this section is kind of going over some simple upgrades that we did. So component layout and that sort of thing. So I'll show you over here, if you can all see, oh no. It's kind of hard to see. Can everyone see this wall over here or no? Okay. So a few simple quality upgrades that we did were the layout of the boards. We used a motherboard system. Continued on from our last semester ECG project. We have our ECG is on the left side, over on this side, and our BP is on this side. We chose to do it this way because it's easier for the clinician or whoever's using the device. It's easier for them to distinctly figure out that this is ECG side and this is BP. And also, as we laid our boards out inside, we also did the same thing inside with our ECG on the left and BP on the right, so it was easier to go to the front panel. And we also have our power boards at the back, and it's kind of hard to see, but we have our power boards at the back, which are here, and our signal boards are at the front up here. And we used a Molex connector, which basically allows you to disconnect and reconnect the boards a lot easier. So we can use it for troubleshooting, or if you need to remove components and that kind of thing. You pull the board out, put it back in after you're done. It's a lot quicker and a lot easier than having to take out, say, 6 boards that are on top of one board and that kind of thing. We also have our 22 gauge galvanized steel EMI protection at the back, which prevents noise from the transformer and the inlet connector. And this also, we also have our resistive screen, or our resistive touch LCD, which will be explained in the other upgrade section because it is a much larger upgrade section. What this allows for is it allows for a lot less space taken up from the other output screens that we were also given to use. Those screens would have taken up, say, about this size if you compact them all together. This one's much smaller, as you can see. And yeah, so that's that section, and I will pass it off to the featured upgrades, which will be a mixture of Eamon, Kush, and Hatham. Or Chicho, sorry, it's Chicho.
So we have, instead of manual 0, we are using a push button auto 0, so which does a 0 automatically with just a push button, except instead of controlling the 0 from the pot. So how it's important, clinically. So as Jeff said and Momo said, usually nurses, they open the transducer stopcock to atmosphere, and that's what, when they open the stopcock to atmospheric pressure, it's gonna, the whole system will show the some voltage in millivolts. So that voltage has to be has to go to 0 to compare to the atmospheric pressure. So without the 0 circuit, pressure signal will be it's not calibrated properly, and the pressure signal will be uneven. It's going to be riding on the offset of atmospheric pressure. Atmospheric pressure is we got a 0 that one down. So we have a short video demonstrating how auto 0 is working.
Okay, auto 0 circuit, tape 2. Here's the circuit.
So right here we have echo junction circuit, and which is we are connecting to 0 circuit, So it's going to acquire the signal and then it's going to feed it to the zero circuit, and the output of the zero circuit will zero the pressure signal. Whether it's static, even if it's a waveform, it's going to zero down the waveform too. So I'm going to
Circuit itself. There's the one-touch button for auto zeroing. And we're going to look at the signal right now. So we're going to apply a zero signal from the simulator.
So you press the zero and press the zero from the front panel.
And now we're going to press the auto zero.
And it will zero the whole.
Brings it up to zero.
And then we're going to change the static.
Now we're going to start changing the static levels. So we're going up.
And then we can press the
And then we're going to auto zero it. There we go. Auto zero.
So usually
And then we're going to put the waveform in. Zero the waveform.
Zero down to, right?
And now we're going to go to do a static zero. Auto zero it. Now go to the waveform. 120/80. Perfect.
So main purpose is so the main purpose of the circuit is to zero down the atmospheric pressure, because atmospheric pressure gonna give an offset to the pressure signal, and if it's not zeroed in the beginning, then pressure signal will be riding on the offset all the time, and then will be the wrong measurement will be done by clinician, and that's wrong diagnostic too, right? So like it has to be zero down when they open the stopcock to atmospheric pressure. So how the circuit is designed? So circuit is divided into the two sections. One with there are like summation. There is one summation amplifier, ramp generator, and control logic circuit. So this is the basic block diagram. So once we press the zero from the patient simulator, then we press the zero button from the front panel control, which is this switch here, and that trigger of the push button will gonna trigger first shot here, and that first shot of 1 second will gonna reset the whole counter circuit, and also gonna trigger the second shot, and the second shot will turn on for around 2 seconds, which will go NAND gate. At the same time, the pressure signal too will be going through the unity gain amplifier, and as there is a voltage comparator, like because the pressure signal will be above zero, it's gonna compare and it's gonna give a output of around like 4 volt, which gonna enable the NAND gate and initiate the whole digital to analog conversion. And as it's gonna start the digital to analog conversion, it's gonna start adding with the pressure signal, and it's gonna keep adding it until it's gonna detect that it is a zero. So basically, the output of a DAC is an inverted ramp signal, which is ramp signal, and the pressure signal is basically positive, where this one is inverted. So as like ramp signal will go down, it's gonna start canceling its offset. So this comparator will detect the zero, and it will gonna stop the whole cycle of running digital to analog conversion, and the pressure signal will flow statically at the output of the machine continuously, unless we open the stopcock to atmosphere, then it's gonna change its static level again, then again we have to press a 0 and 0 down that atmospheric pressure. And this is the schematic. So as I said, this is the input. It's going to take a signal, a pressure signal at the input, and the pressure signal will go to adder right there, and it's going to add with the DAC, digital to analog converter here, and it's going to compare until it's going to detect the 0. So basically the whole cycle of comparing the 0 is controlled by this generator pulse control circuit. And I'm going to pass it to the team.
All right, thank you. I'll take this. Okay, so I'm really excited about this. Got to work on a new part of the project this year, which is the front-end display. So we used something a bit different from all previous years. Usually there's panel meters, and panel meters are basically voltmeters. So they take in a voltage signal, and it's already pre-programmed to output what that voltage signal is. So instead of having a voltmeter, we've got a compact size, probably about 3 inches wide by 1 inch high. We decided to do something a bit different in hopes of kind of inspiring first and second years to do something different in the future. Anyhow, this is what we used, which is a 3.2-inch resistive touch LCD screen. This is made by 4D Technologies, and its programming is provided by the Arduino. And it's the Arduino Uno that we used. It was graciously allowed, graciously given to us and borrowed our loan programming, so thank you very much for that. So we use this along with a student from the mechanical engineering side, so there's a lot of interdisciplinary help, I guess. So we worked closely with Tom Moulton, who's here. I just want to say thanks again. It was great to get a lot of the coding hashed out with them. Unfortunately, in our year, we didn't have a lot of experience with Arduino or programming. A lot of our experience has been with electronic circuits and digital design, and this is a bit different, but I heard it's being introduced for first year. So because of that, that means a lot of people have the opportunity to perhaps expand on this design and not just stick with the easy to do, easy use, and kind of cheesy display of a panel meter. So anyhow, the next screen here shows the Arduino acting with an intermediary, which is the shield. So this here, this little red device, is a shield that goes on top of the Arduino, and it connects the Arduino programming controller to an LCD display, or LCD display screen. So this is basically what communicates with the Arduino and the output. So go to the next one. So they've made it very easy, 4D Systems. They have a program called Workshop Busy Genie, and this one is very user-friendly. So you've got a lot of people that don't know about programming, or they're not able to program, and they can use this to point and click basically a lot of the front panel design. So what you see there with the logo, with the digital display, is provided mainly by this program, and basically the sky's the limit with this. This year, because of the inexperience and lack of education that we've had so far with this kind of technology, I wasn't able to get as much done as possible, but we got quite a bit done. In future, for a lot of the students that are here today, you can get many menu options. So because it is resistive touch, you're able to touch a point on the screen and load up a new menu. So for example, you can have, say, a systole and diastole going to attack your bradycardia, or high blood pressure or low blood pressure. You could have an alarm system automatically come up that has to be acknowledged by a touch of the screen. That eliminates many buttons, and it eliminates many of the analog inputs. So basically the only analog input would be the human, and everything else would be digital. So I'm guessing in 2 years, if first year students worked on this, there's 7-inch displays available right now, and I think 10 or 12-inch could be available in 2 years, which are all resistive touch, made by 4D Systems. And if that's available to them, I'm sure the whole front panel could be digital. You wouldn't have to worry about knobs and buttons and switches and all these archaic things. So it is good for learning, and it's awesome to apply knowledge, but right now this is what we use, and yeah, you can see the output here. We'll do some demos later with it as well. So this is the code. This is Arduino coding. Again, worked on this with Tom, mainly his creation. And the screen will load this, and it basically looks at the Arduino. The Arduino says, do this, do this, do this, over and over and over again. And as it rolls through the coding, it will output on the display. So for example, we have 1.2 volts coming in from our circuits, and those 1.2 volts represent systolic. That's fed into the Arduino through this coding and output to the screen to show 120. So we just remove the decimal, add a 0, and we've got 120 systolic over 80, which is also represented by 0.8. Yeah, so again, hopefully a lot of the upgrades in education in the school will let students become more familiar with this. It looks complex, but realistically, anybody can learn it. And there's a lot online, there's a lot of manuals, a lot of information and education. And a lot of smart students that are in the school that can definitely help anybody with this. I'm going to pass this on to Gijo, and he's going to speak about alarms for the valence method.
Hi everyone, my name is Gijo. I'm going to talk to you about alarms in section B. Basically, valence 100 IDP machine has mainly two alarms for systolic and diastolic. The alarms will continuously monitor the pressure values, and if it goes beyond the normal value, alarms will be triggered. The alarms have both audible and visual indications to clinical staff during emergency situation. Now, Evan will help in demonstration. So, for the systolic alarm, we have mainly two limits, an upper limit and lower limit. When the pressure value goes below 100 mm of mercury and above 140 mm of mercury, the alarm will be triggered. Same in the case of diastolic alarm also, we have two limits, an upper limit and lower limit. When the pressure range goes below 60 and above 100, the alarms will be triggered. Now Evan will demonstrate for it. So when the alarm is, when the pressure value reaches close to the alarm range, it will give a warning. Then when it goes beyond the range, it will continuously give an audible sound and LED display. Showing beep sound is showing when the pressure value is close to the range. Same in the case of diastolic also. You can see that in the diastolic. So, in case if the alarm is triggered by pressing a mute button, we can make the audible alarm silent for 30-second duration. If the alarm is in mute condition also, the LED will provide indication of which alarm is triggered. The reason why we use 30-second mute instead of a permanent mute switch is because if you use, the clinician has to acknowledge the critical patient situation and cannot ignore it or permanently disable the alarm. For example, during a nurse shift change, a nurse may not be aware that the permanent mute is active, so he cannot make a correct diagnosis. Moreover, the valence method will give preference to patient safety as number one.
So this is currently on mute, and as the pressure arrives back at normal, you see on the screen here, 120 over 80, the alarms go off, and the indicator also goes off.
There is a mute indicator also that will display the status that the alarm is in mute condition. And this is the schematic alarm schematic, and we have inputs for systolic and diastolic, and it will goes to a window comparator circuit where it is compared, and the output is fed to the alarm circuit through optocouplers, and the alarm circuit we have a 555 timer IC for controlling the timing, and then based on the timer the alarm will be, buzzer will be working. Next, which will talk you about miscellaneous.
So in this section we have, in section I, if the judges can turn to that page, and then they could also please come up to the front and around the device, and Egan's going to go through a few of the components that we have. Is it on? Yeah, it is on that sheet. So this sheet does look like this, and then the rest of the audience, could you please stay seated and come up at the end of the presentation, and you guys can all take a look after that.
Come on up.
So
We're just going to go through the
we'll go through a few of the components that we do have. We do have a detachable hospital grade cord, which also has a EMI protection introduced in the block. There's pass-through bushings through the EMI protection at the back. There is EMI protection in 3 locations, which is the inlet, the power cord, as well as the EMI protected galvanized steel. And there is also an EMI choke on the AC wires. There is 2 double pole single throw switches, one on the back to turn the device on, and there's also one in the front to turn off and on the beats per minute sound. There's many of relays in this. I think throughout a few of the boards, I think there's about 27 relays in total. There are power indicators letting you know that the device is on. There's one on the front. And then there's many different types of tie wires. We have a few that are mounted on the sidewall and a few that are actually on the bottom of the device. There's 2 different colors of heat shrink. There's a red and black. And we also have 3 different colors of wire. We have red and blue, blue, and a red. What? Oh. Sorry. And the enclosure, it does not stand on 4 rubber feet. The enclosure actually, it stands on a pole that is electrically isolated from anything that will, it's actually a hospital grade. And all controls in the front are non-conductive, they're made of plastic and that sort of thing. And then as a bonus, we have our LCD touch screen, which can be integrated into a touch component.
Yeah, because we were into that. It's something I'll look into. How much cheaper is it? More compact. For $160, we got a screen shield adapter.
Okay, sorry judges, we're going to have to speed this up. We're kind of running out of time here.
We can always look at it after.
Yeah. So this is the rest of the project demo that doesn't touch on any, the other sections.
So we were told that we took about an hour, so we're going to go through additional circuits, a map circuit and the BPM circuit, and Kush is going to show a video. So map measurement, it's main arterial pressure. It's observed on, for example, on blood pressure waveform, and that's on the arithmetic average of systolic and diastolic pressure values. And you can find the map using this equation, which I made it as this here. So this is the input, systolic and diastolic going into the subtractor. And the same here, we're going to have subtraction and plugging into an amplifier, which we're going to have the third leg of the gain. And then it goes to here where addition will happen, and goes to the inverter, and we'll have like 93 millivolt if you're plugging in 120 millivolt and 80 millivolt.
Like plug number.
So we should not talk
So
about
this
the
is the
BMTY
bits
circuit.
per minute circuit, and basically the frequency response of the fracture signal is like it says 2 Hertz. So basically the circuit it takes the frequency and it converts the frequency into the voltage. Because the frequency is too low, we need to amplify. We need to multiply that frequency by 100 or 1000. So basically, we are taking the pressure signal and we are converting that pressure signal into the pulse waveform, and we are multiplying with the frequency amplifier circuit, and that frequency amplification can be converted into the voltage. So bits per minute, I have a video.
We also have an audio,
So we have like big indicator.
so you know that your heart is listening.
And there's a small video I have here.
Okay, this is take 2 of our temperamental beats per minute circuit. So if you can show the audience, there's the simulator right there. And so the signal is coming into the acquisition circuit. And then it's going through to the auto 0 circuit. So the waveform we've got right now is just our standard 120 over 80, and it's doing quite nicely. And to get the beats per minute, what we have to do is we take that, we run it through a comparator to get a square wave, and then we have to multiply it. So we have a multiplier circuit, and then we feed the multiplied frequency, so it's sort of like a 10 times 10, into a chip that converts frequency to voltage. So, and then we read the voltage out as a beats per minute. So it's kind of like if we put in, right now the waveform is at 80 beats per minute. If we put in that 80 beats per minute, we should get out 0.8 or 800 millivolts. You should get out 800 millivolts. So let's see what's going on with the frequency multiplier. Can we show that frequency multiplier on the scope? Okay, so it's taking that low frequency and multiplying it. I'll just change the time division so we can see it a bit. There we go. And so that is going into the frequency to voltage chip. And as you can see here, what we're getting out from that is 860 millivolts. The problem that we found is the phase lock loop frequency multiplier circuit can be unstable. So it can all of a sudden stop multiplying and for a space of time just go like right to saturation, which can mess up our output. Okay, yeah, we're going to change. We'll change the actual beats per minute to 100 beats per minute, and as you can see, it's a little bit unstable, but it's going up to around almost 1 volt, which is what we want. And then we're going to 120 now. And it's increasing. Very good.
So I'll leave it to Jeff to introduce the secondary students from the party.
Hi again. As part of the Team Valence project and learning experience, we worked with the second year group. Valence taught a side project in addition to the Valence 100 that we wanted to have. I then met up with the manager of the second year group, Dan, and proposed the assignment. The assignment was make a mock-up demonstrating how the transducer for an invasive blood pressure monitor works. Dan and I and other group members met on a weekly basis. The result was extremely beneficial on both sides. The edge group did very well in consistently providing weekly updates, coming up with innovative solutions, and staying on target in implementing and demonstrating these solutions. It's been a pleasure working with them, and with that, I would like to introduce Nick and Faray from the second year group.
Thank you, Chuck. Hello and good afternoon. We are the second year group assigned to Jeff's group to do our part for the final project. Before we begin, I'd just like to introduce ourselves. I'm Nick, this is Faray, our manager Dan, Amanda, Farhad, Lucy, and Jane. So what we were trying to do was to design and build a blood pressure mock-up simulator using the skills and the knowledge that we acquired. We were also assigned to build or write operator's manual and service manual for any other device. As before, they're supposed to be a slide. As Jeff showed before, they're the transducer slide with the picture underneath. What we original design was to use an acrylic tube filled with artificial blood and using a syringe to pressurize it with a diaphragm on the top. The transducer would then be mounted in the fluid as well to read any pressure readings. But that was not our final design, and I think we'll pass on to Faray to show the final design.
All right, so I'm Faray, as I mentioned before. So this is our final design. It's much simpler as compared to before. This is something we're always trying to do in healthcare technology, making it more simple, more easy to use, easier to implement. So in this case, the acrylic tube is replaced by the IV bags. As we can see over there, the IV bag hanging. So this IV bag contains liquid. This would be blood in the transducer. Then the IV bag, when we mechanically move the IV bag, the sensor on the top moves. The sensor is a strain gauge or a flex resistor. So the resistance changes as it's flexed. And then that is taken to a bridge circuit, which translates the resistance change into voltage change. And that is then sent back to the monitor through the cable. Always we have to, of the bridge circuit, we always have to adjust the zero baseline, just like they have to adjust the pressure on the normal blood pressure monitor. So we had a pot for that. We replaced it with a bigger pot, as we can see on the transparent box. That's our bridge circuit. So, as I said before, the bag is the diaphragm, and on top is the flex sensor, which will be the transducer. And as we press it and change its resistance, it's translated into voltage difference. And you can see the output right there. And it also triggers the alarm.
Beats per minute indicator. Yep.
Yeah, that's the beats, and all the alarms are going off because with this way we can test the full range of the device, all the way from 0 to the maximum, and the VSATs and everything. And that's what we did, and we would like to give it back to each other.
Just a quick note about the alarm system. Because our alarms have a certain range for reading high systole or low systole, high distole or low distole, with the secondary project, it's always starting at 0. It's a 0 line, just to show the potential for calibration. So our alarms are always signaling off until the frequency of the bag squeezing gets up to speed.
So the pot's 4 to 0, that the line before it begins.
Thanks, Ray. In conclusion, I would like to thank the judges for coming and giving us such good marks. Conclusion Team Balance would like to acknowledge the support and help and guidance of Dave McKay, Dave Schmidt, Richard Tidman, Tom Moulton, Sandra Kudla, and Loren Fuentes. Thank you. All the staff of the Office of the School of Science and Engineering Technology, you have helped us in innumerable ways throughout the year, especially letting us into the labs. You're the best. And to all our classmates, thank you Team Triforce, Team Genesis, and the Bioradicals. Thanks everyone.